to everyone, welcome once more to another video in our YouTube channel. So in today's video we are going to continue looking at the tutorial questions on recursive sequences and series, and specifically we are going to be solving June 2020 further maths paper 2. So for those of you who have not watched the previous videos, part 1, part 2 and part 3, and is able to watch them, you can get to the channel playlist on and you check on the further maths playlist and you're going to see the various videos. Nevertheless, I'm going to include the links to those videos in the description and also in the comment section, so that for those of you who have not watched, you watch it. Now, those of you who are just joining us, endeavor to subscribe before leaving. If the video is good, make sure you like the video. If you have difficulties, make sure you comment in the comment section the difficulties that you face. So let's get started. Okay, so we are going to start straight away with solving of the various problems. So we have some informations that were displayed to us. We have u0 is 1, u1 is 3, and un plus 1 is 3un plus 4un minus 1. Now, the very first question is asking us to find the value of u2. So to find u2, I will simply come to this recursive relationship and I fit n equal to 1, since I have information about u0 and u1. Because if I fit n equal to 1, the left hand side will become u2, the right hand side will become 3u1 plus 4u0. Alright, so doing that, I get my u2 to be equal to 3u1 plus 4u0. u1 is 3 and u0 is 1. So substituting and simplifying, we get 9 plus 4, which is 13. So our u2 is equal to 13. Now, Woman 2 is asking us to show that un plus 1 minus 4un is equal to negative 1 raised to the power n times u1 minus 4u0. Alright, so what is un plus 1 minus 4un? Un plus 1 minus 4un is equal to, the first two terms here represent un plus 1 because it was given originally 3un plus 4un minus 1. So I'm just going to replace un plus 1 with 3un plus 4un minus 1, then minus 4un. So I bring like terms together. 3un minus 4un is negative un. So finally we get negative un plus 4un minus 1. So we can pull out the negative sign and we get negative into un minus 4un minus 1. Now let us come back to the original proof. We want to prove that un plus 1 minus 4un is equal to negative 1 raised to the power n times u1 minus 4u0. It is clear that that this right hand side of the proof is an expression of a geometric progression. So since it is an expression of a geometric progression, it means that the left hand side is a certain sequence which is a geometric progression, because u1 minus 4u0 has a value. We know that our u1 is 3 and our u0 is 1. So we can calculate the value of u1 minus 4u0. So if you calculate that value, it means it is maybe just going to be the first term of that sequence, and then the common ratio is negative 1, and then we are raising it to the power n. That is how we can interpret the proof. So with that, we can clearly let that sequence, maybe this what we want to find as tn plus 1. So maybe letting this to be tn plus 1, it means our tn plus 1 is un plus 1 minus 4un. And then we should have in the back of our mind that at the end we need to get this right hand side of the proof to be the same as tn plus 1, meaning we need to express tn in terms of n. Alright, So having Tn plus 1 as un plus 1 minus 4un, it means our T of n is equal to un minus 4un minus 1. Why are we looking for T of n? Because we want to take the ratio between Tn plus 1 and Tn, since we have discovered that the left hand side of our proof is a geometric progression. Now we actually need to verify if it is true, because clearly the common ratio is -1, and then the first term or the zeroth term is u1 minus 4u0. Alright, so Tn plus 1 being equal to the left hand side means that Tn, I will just decrease the n terms, the terms in n by 1, so I will get Tn to be un minus 4un minus 1. So if I do the ratio between Tn plus 1 minus Tn, or we can our Tn plus 1 is equal to 3un plus 4un minus 1, then minus 4un, because our un plus 1 is equal to 3un plus 4un minus 1. So replacing un plus 1, since this is the expression of Tn plus 1, we are going to finally get negative into un plus 4un minus 1. Alright, so from there we get our Tn plus 1 to be equal to negative into un minus 4un minus 1. This is even it here, negative into un minus 4un minus 1. Since this left hand side is still T of n plus 1, then definitely we should have the same thing. So this interior here is just equal to what? Negative of our T of n, because in the T of n here, if we factor out the T of n here, it is just this interior. So it means that our T of n plus 1 is equal to negative T of n. So divide both sides by T of n, we are going to get T of n plus 1 divided by T of n to be equal to -1. And this is the common ratio of my geometric sequence T of n, because if we want to show that a sequence is geometric, we need to show that the ratio between the n plus 1 term and the n term is equal to a constant. In this case, the constant is -1. So from there, we can express our T of n in terms of n. So T of n is a geometric progression. The common ratio is -1. Now the very first term is what? T1, and T1 is u1 minus 4u0. Because to look for T1, I simply need to let n to be equal to 0. So T1 will give me u1 minus 4u0. So I see it clearly. So we can now express our T of n in terms of. Alright, so since we have seen the characteristics of the sequence Tn, our Tn is a geometric progression of first term T1 and common ratio -1. Now our T1 was u1 minus 4u0. Alright, so we can express T of n in terms of n. Since it is beginning from 1, it means our T of n will be equal to T1 r raised to the power n minus 1. Our T1 is u1 minus 4u0, and then our r is -1. So I need T of n plus 1 because it was the left hand side of my proof. So my T of n plus 1 becomes -1 raised to the power n times u1 minus 4u0. But my T of n plus 1 was u of n plus 1 minus 4un. It means that my u of n plus 1 minus 4un is -1 raised to the power n times u1 minus 4u0. Okay, the next part of the equation, Roman 3, is asking us to express u of n plus 1 in terms of u of n. Now, since you have proven the relationship here, our u of n plus 1 minus 4un is -1 raised to the power n times u1 minus 4u0. It means our u of n plus 1 is just gotten by adding 4n on both sides of the equation, 4un on both sides. So our u of n plus 1 becomes -1 raised to the power n times u1 minus 4u0 plus 4u of n. Alright, so we continue. Roman 4 is saying we should show that u of n is divergent, or showing that we are showing that u of n diverges. Okay, so we have our relationship that we proved earlier. We proved that u of n plus 1 minus 4u of n is equal to -1 raised to the power n times u1 minus 4u0. So we are going to prove by contradiction. It means that we are going to suppose that the sequence converges, and then we prove that it is impossible for that supposition to be true. Proving that it is impossible for it to converge, whereas supposing that it converges, creates a contradiction. So a sequence un converges if its limit is finite and unique. Mathematically, we mean that there exists, if there exists a unique limit in the set of real numbers, such that the limit of the sequence, of the sequence un is equal to that value, then the sequence un converges. Okay, so since I suppose that it converges, it means I can take the limit on both sides of this equation. So the limit as n tends to infinity of the left hand side will be equal to the limit as n tends to infinity of the right hand side. But the limit as n tends to infinity of the left hand side is the limit of u of n plus 1 minus 4 times the limit of u of n, because I suppose that the limit of u of n exists, meaning that it converges. Okay, so if I have a sequence u of n, if it converges, then u of n plus 1 and u of n have the same limit. It means that as n tends to infinity, the limit as n tends to infinity of u of n plus 1 is the same as the limit as n tends to infinity of u of n. So maybe I call that limit to be L. So here I'm going to replace it with L, and here I'm going to replace with L. It means that this guy here give me L minus 4L, which is negative 3L. I can call that equation 1. Now this limit, that is the limit of u of n plus 1 minus 4 times u of n, is equal to this limit, because the two are the same since we proved it. So at the end, since we know u0, we know u1, you can get the value of u1 minus 4u0. Simplifying, you get negative 1. So we just replace here this guy here with negative 1, and we maintain this. Now we can pull out the negative 1 outside, and we get negative. It means that this limit is equal to negative the limit as n tends to infinity of negative 1 raised to the power n. Now let's see a trick here concerning negative 1 raised to the power n. Negative 1 raised to the power n has only two values. It is either 1 or it is negative 1. If I'm raising it to an odd number, it's going to give me negative 1. If I'm raising it to an even number, it's going to give me 1. So negative 1 raised to the power n is negative 1 if n is equal to 2k plus 1, meaning that it is odd. It is equal to 1 if n is equal to 2k, meaning even. So at the end, we see that this limit is going to give us, since n is tending to infinity, n can be either odd or even. So we put both limits. So this negative sign remains outside, then the limit of this guy here is plus or minus 1. So it now depends on the value of n. But n is tending to infinity, we don't know if it is going to be odd or even. So we put odd or even. Alright, so negative times plus or minus becomes minus plus 1. That's equation 2. So equation 1 will be equal to equation 2 because the limit of this guy is the same. So the limit of this guy is negative 3L in equation 1, and the very limit is minus plus 1 in equation 2. So those two equations are the same, meaning that negative 3L is equal to minus plus 1. So we can divide both sides by negative, and we are going to get L to be minus plus 1/3 or plus or minus 1/3. So we can conclude that what L is equal to negative 1/3 if our n is odd, and then it is 1/3 if our n is even. So we see that what that the limit of this sequence depends on the value of n. So if n is even, the value gives us 1/3. If n is odd, the value gives us negative 1/3. So it is contradicting the uniqueness property, because it belongs to the set of real numbers, because negative 1/3 and 1/3 belongs to the set of real numbers. But now it is not, the limit is not unique, because it has two different values depending on the value of n. But our condition here is that what for all values of n, meaning as n tends to infinity, the limit should give us L, and L should be unique. So we can conclude that what it diverges, since we suppose that it converges, and according to our supposition that it converges, it means it should have a unique limit. And then at the end, we don't have a unique limit, meaning the contradiction has been set up. So we can conclude that it diverges, sorry. Okay, so we are going to proceed with the next question, which is Roman 5. It's asking us to show that u of n is greater than or equal to 1 for all values of n greater than or equal to 0. So we are going to prove this by mathematical induction, where we are going to let P of n be the statement u of n is greater than or equal to 1 for all values of n greater than or equal to 0, and then we prove using the various steps. Okay, so useful informations. Our u of n plus 1, our u0 is 1, u1 is 3, u1 minus 4u0 is negative 1 after simplification. So it means our u of n plus 1 minus 4u of n is negative 1 raised to the power n times negative 1, because this negative 1 here was u1 minus 4u0. Okay, so if we multiply these two, since they have the same base as negative 1, we can just add the powers. So it means our u of n plus 1 minus 4u of n is negative 1 raised to the power n plus 1. Alright, so we need to prove this statement we need to prove that u of n is greater than or equal to 1 by contradiction. So this is our statement. So we begin verifying if the statement p0 is true. So for the very first value of n, that is n equal to 0, because here n is greater than or equal to 0. For n equal to 0, my statement p0 should be that u0 should be equal to 1. You see, because according to originally we have our u0 as 1, and here u0, we are proving that u of n is greater than or equal to 1. Our u0 is 1, and since 1 is greater than or equal to 1, it means that u0 is greater than or equal to 1. So it is true for n equal to 0. Now we set up an induction hypothesis by assuming that the statement p of k is true. So it is true for n equal to k. If it is true for n equal to k, we just come here and we replace n with k. We are going to get u of k is greater than or equal to 1. So we are going to use this supposition to prove that it is true for n equal to k plus 1. This step is called the induction step. Now, proving that it is true for n equal to k plus 1, it means we need to prove that u of k plus 1 is greater than or equal to 1, because true for n equal to k means u of k is greater than or equal to 1. So proving true for n equal to k plus 1 is the same as proving that u is actually proving that u of k plus 1 is greater than or equal to 1. But to prove that u of k plus 1 is greater than or equal to 1, we need u of k. So we need to find the expression of u of k in terms, the expression of u of k plus 1 in terms of u of k, because we are going to use our induction hypothesis to prove the induction step. Alright, so according to this definition, we can add 4u of k on both sides of the equation, because here we can just replace n with k, and then since it satisfies, we are going to get u of k plus 1 to be negative 1 raised to the power k plus 1 plus 4 u of k. Now, this is the importance of the hypothesis. We see that we have information about u of k, and that is the information that we are going to use to prove this inequality. So to get my u of k plus 1 in terms of u of k, in order to introduce an inequality, I need to begin with that inequality. See, this is what we are going to do. Our u of k is greater than or equal to 1 according to our induction hypothesis, which we assumed it was true. So my aim is to get u of k plus 1 at the end. You see, so to get u of k plus 1, I will begin with what I know. I know information about u of k. It means that to get u of k plus 1, I will first of all multiply u of k by 4, and then I'm going to add this guy here so that I get my u of k plus 1 directly. So u of k greater than or equal to 1, I multiply both sides by 4. I get 4u of k is greater than or equal to 4, and I'll add this on both sides of the equation, that is negative 1 raised to the power k plus 1. Adding it on both sides, we get this. Now we are left now to deal with this, because we have already introduced this inequality sign, you see. But now our objective is to prove that the left hand side, which is in red, which is u of k plus 1, is greater than or equal to 1. So it is not in function of k. So I need to make sure, I need to dissolve this negative 1 raised to the power k plus 1. I introduce an inequality where k is going to cancel. Alright, so negative 1 raised to the power k plus 1 has two values. It is negative 1 if k is even, and it is 1 if k is odd. Alright, so I see that that the minimum value of negative 1 raised to the power k plus 1 is negative 1. That's the minimum value. And then the maximum value is 1. It has two values. So since its minimum and its maximum is 1, it means it lies between negative 1 and 1. Since it lies between negative 1 and 1, what I am my main concern is, because if I want to remove negative 1 raised to the power k plus 1 from this position, then I need to bring in something that negative 1 raised to the power k plus 1 is greater than, so that the inequality is still going to hold. Because if I bring something that this guy is less than it, then this inequality is not going to hold again. So I need to bring in something that this negative 1 raised to the power k plus 1 is greater than, so that my inequality continues as greater than. Alright, so I'm going to concentrate now on negative 1 is less than or equal to negative 1 raised to the power k plus 1. Because if negative 1 is less than or equal to this guy here, it means that negative 1 raised to the power k plus 1 is greater than or equal to negative 1. So from there, I'm just going to replace negative 1 raised to the power k plus 1 with negative 1. It is not equal to, but the inequality is greater than or equal to. Alright, so working the right hand side, I get 3. So my left hand side is u of k plus 1. So my u of k plus 1 will be greater than or equal to 3. But since 3 is greater than or equal to 1, it means that my u of k is greater than or equal to 1, because my u of k plus 1 is greater than or equal to 3, and 3 is greater than or equal to 1. Hence, my u of k plus 1 is also greater than or equal to 1. Alright, so Roman 6 is asking us to show that the sequence u of n is increasing. So to show that the sequence is increasing, we just need to show that what? That u of n plus 1 minus u of n is greater than or equal to 0. Now this is our u of n plus 1 that we had earlier. So having that u of n plus 1, we need to show that what u of n plus 1 minus u of n is greater than or equal to 0. So we need the expression of u of n plus 1 minus u of n. So u of n plus 1 minus u of n is this. This is u of n plus 1 then minus u of n. So for u of n minus u of n gives us 3u of n, then plus now negative 1 raised to the power n plus 1. So we need to introduce this inequality. We need to introduce that inequality. Alright, so since our u of n plus 1 minus u of n is equal to 3u of n plus negative 1 raised to the power n plus 1. Now we need to introduce some inequality so that we should get an inequality here, no more an equality. So in the previous question, we proved that u of n is greater than or equal to 1, and then we also saw that what negative 1 raised to the power n plus 1 is greater than or equal to negative 1, because negative 1 is less than or equal to negative 1 raised to the power n plus 1. It's the same thing. Alright, so from there, automatically I can change this equality sign to an inequality sign, and then I replace the respective values there. So in the place of u of n, I'm going to replace it with 1. Remember, I am changing the equality sign to an inequality sign. That is why I can just replace the upper bounds of these guys. So changing the equality sign to an inequality sign, my 3 remains. My u of n, I replace it with 1, and then negative 1 raised to the power n, I replace it with negative 1. So I simplify, I get u of n plus 1 minus u of n greater than or equal to 2. But I know that 2 is greater than 0, and u of n plus 1 minus u of n is greater than 2. It means that u of n plus 1 minus u of n is also greater than 0, since 2 is greater than 0 and it is greater than 2. So I can draw a conclusion, but in layman's sense, u of n plus 1 is greater than u of n. So u of n is increasing as a conclusion. So we can conclude that the sequence u of n is increasing. Alright, so Roman 7 is asking us to show that v of n and w of n are geometric. That's what it's asking us to show. So my v of n is equal to u of n plus u of n minus 1. It means that my v of n plus 1 is equal to u of n plus 1 plus u of n. Now v of n is geometric means, showing that v of n is geometric, we need to show that the ratio between the n plus 1 term and the n term is equal to a constant. Alright, so the n plus 1 term, that is u of n plus 1 plus u of n, I will replace, originally I have highlighted this in red. So u of n plus 1 was 3u of n plus 4u of n minus 1. So my v of n plus 1 becomes 3un plus 4un minus 1, then plus u of n. Now I can add 3un to un to get 4un. So at the end, I can factor out the 4 and I will get v of n plus 1 to be 4 times u of n plus u of n minus 1. But this in blue is what our v of n. So we can say our v of n plus 1 is equal to, since it is u of n plus 1 plus u of n is equivalent to 4 v of n, since this guy here is v of n. So it means v of n plus 1 equal to 4 v of n. So v of n plus 1 on v of n is equal to 4, which is the common ratio. So we are proving that it is a geometric progression. Now, proving that w of n is geometric, we do the same thing. Our w of n was u of n minus 4u of n minus 1. It means our w of n plus 1 is u of n plus 1 minus 4u of n. Alright, so with that, we get our w of n plus 1 to be, our u of n plus 1 I've highlighted is 3u of n plus 4u of n minus 1, then minus 4u of n. Alright, so 3u of n minus 4u of n is negative u of n, then plus our 4u of n minus 1. I can factor out the negative sign, and then what is in red is still wn. So it means our wn plus 1 is equal to negative wn. If you're vigilant, you see that what this wn plus 1 was our sequence t of n plus 1. So you see that the equation was not difficult. They gave you what to use, but in another subpart, that is, if you could already identify this guy, you could just use it to prove Roman 2, because I believe Roman 2 was maybe very confusing to prove to some of you, and also the Roman 3, which is asking us to prove Roman 4, which we use mathematical induction. So you see that the answer to the equation was in the equation. You were just supposed to be vigilant. So our W of n plus 1 is equal to negative W of n. So W of n plus 1 over W of n is equal to negative 1, which is our common ratio. So we are proving that W of n is also geometric. Alright, so Roman 8, we are expressing un in terms of n. That's what we are doing. Actually, Roman 8, we are expressing Vn and Wn in terms of n. So we should be very careful with the equation here. I made a typing error. So our Vn is V1 r raised to the power n minus 1. Since it was geometric, our common ratio was 4. Our first term is u1 plus u0. We just replace the values and we get it. Now our W of n is the same as t, is the same as the sequence t of n. So that's it. You just replace since you have the common ratio. Alright, now this is actually Roman 8 asking us to express u of n in terms of n. So this was asking us to express u of n. This Roman 8 was asking us to express v of n and w of n in terms of n. And then this is hence express u of n in terms of n. Now we're giving u of n plus 1 plus u of n minus 1 to be v of n, and then u of n minus 4, u of n minus 1 to be w of n. But since you have found the expressions of v of n and w of n, we just replace. So this will be equal to 4 to the n, and this will be equal to negative 1 raised to the power n. Now we need to look for u of n, you see. So if we subtract both equations, you are going to have something only in terms of u. So subtracting, take equation 1 minus equation 2. This is going to give us 5u of n minus 1 on the left hand side. Right hand side is going to give us 4 to the n minus negative 1 raised to the power n. So our u of n minus 1 will give us 1/5, dividing both sides by 5, times 4 to the n minus negative 1 raised to the power n. But now we need u of n, so we increase the n by 1. So our u of n will be equal to, in the place of n, I replace with n plus 1. In place of n, I replace with n plus 1. So we can conclude that our u of n is equal to 1/5 into 4 to the n plus 1 minus negative 1 times negative 1 raised to the power n, because negative 1 raised to the power n plus 1 is negative 1 times negative 1 raised to the power n. So at the end, the two negatives gives us positive. So we have our u of n to be equal to 1/5 into 4 to the n plus negative 1 raised to the power n.